In this lecture, we will discuss chemical reactions and the importance of carbon. Here are two substances, highly reactive sodium and water. If we put them together, neat things happen. A chemical reaction. In reality, the reaction of these chemicals is amazing, and you can watch a video on this in the Activities folder. We can represent the reaction with a chemical equation. Not as exciting, but still very important. On the left we have the reactants, those atoms or molecules that will react, sodium and water. And on the right, the products of the reaction, sodium hydroxide and hydrogen. Now, notice the numbers in front of some of the reactants and products. These are called coefficients. They are needed to balance the equation. 2 sodium atoms and 2 water molecules are needed to produce 2 sodium hydroxide compounds and 1 hydrogen molecule. We have 2 sodium atoms on the reactant side and product side. We also have 4 hydrogens and 2 oxygens. Balanced. But if we were to try this reaction out in a lab, how would we know the exact amount of reactants to add for the reactions to occur properly? We would need a really tiny pair of tweezers to count out atoms and molecules. Luckily, we don't have to do that. Let's look at this equation. Hydrogen and oxygen combine to form water. But how much hydrogen and oxygen do we use? Well, in a lab, we use moles. No, not those kind of moles. This kind of mole. 6.022 times 10 to the 23rd. That number is a mole. That is a really big number, right? Why is this number special? A mole is just a unit of measurement. It is 6.022 times 10 to the 23rd bits of anything. But here's the neat part. If you weigh out the atomic mass of an atom or molecular mass of a molecule in grams, you will have 1 mole of that substance. Need an example? Okay. Let's say we have some pure gold. It's an element, right? If we want to have 1 mole of this pure gold, how many gold atoms would there be? Right. 6.022 times 10 to the 23rd gold atoms. Because that's what a mole is. But how much would that mole of gold atoms weigh? That's a little trickier. We have to know the mass of a gold atom. If we look at our periodic table, it is 197 atomic mass units. So all we need to do is replace the atomic mass unit with grams, and a mole of gold weighs 197 grams. Yay! All life forms are carbon-based. This is due to the bonding characteristics of carbon. Carbon has 4 valence electrons and can complete its outer shell by forming 4 covalent bonds. It can form 4 bonds with 4 hydrogen atoms to produce a methane molecule. This is the simplest hydrocarbon. Hydrocarbons consist of only carbon and hydrogen atoms. Or we can add another carbon atom with hydrogens, and this is ethane. And we can keep adding carbons. As you can see, covalently bonded carbon atoms can form a backbone or skeleton that other atoms such as hydrogen can bond to. When we see molecules with carbon skeletons, they are likely to be organic molecules. Organic molecules are made by living organisms. In biology, we use a special word for the creation of molecules: synthesize. Now, hydrogen is not the only thing that can be added to a carbon skeleton. Other atoms can be added, but in organic molecules, we are most concerned with special groups of atoms called functional groups. There are many functional groups, but you're required to know only 6 of them. The first is hydroxyl. It consists of an oxygen bonded to a hydrogen atom. The R represents the organic molecule. Since this group has an electronegative oxygen, it has the property of being polar. It may also lose its hydrogen in solutions with a pH of 7 to become an ion. The carbonyl functional group consists of a carbon double bonded to an oxygen. The oxygen makes this group polar as well. Carboxyl consists of a carbon double bonded to an oxygen and single bonded to an oxygen with a hydrogen. This group tends to be acidic in solutions with a pH of 7. As the hydrogen dissociates from the molecule. The amino group has a nitrogen bonded with two hydrogen atoms. It tends to act as a base because it binds with hydrogen ions when in a solution with a pH of 7. Remember, if a substance decreases the hydrogen ions in a solution, it is a base. Sulfhydryl consists of sulfur and hydrogen. It has a tendency to form disulfide bonds with other sulfhydryl groups. We will explore these bonds more later on in the class. And the phosphate group has a phosphorus double bonded to an oxygen and single bonded to 3 other oxygen atoms. Phosphate groups are negatively charged at a neutral pH and can store large amounts of energy in their bonds, especially when multiple phosphate groups are connected to each other. So let's redecorate this boring hydrocarbon and add some exciting functional groups. Let's first add a nitrogen with 2 hydrogens. Which functional group is this? Yes, the amino group. And what kind of property does it have in a neutral pH? Yes, it acts as a base, taking up hydrogen ions. What is this group? Yes, hydroxyl. And what property does it have? Yes, the oxygen is highly electronegative and makes the group polar. And what is our last group? Yes, phosphate. And phosphates have high energy bonds connecting the functional groups. These functional groups can give molecules interesting properties